Now with this lesson, we want to look at sign diagrams some more, but I want to look at an element of this that we didn't have in our first lesson, and that is what are some other things that can impact whether we're increasing and decreasing, and particularly when we have limitations on our domain. Okay, here we have a rational function, and you can see here we have this x cubed plus 3x squared minus 4x minus 12 all over x squared minus 9. And you guys, from what you've learned about rational functions in the past, you know that you can factor. If we were to factor our numerator by grouping, we'd have x squared times x plus 3 minus 4 times x plus 3. Our denominator would factor with difference of squares, x plus 3 times x minus 3. Okay. We have an x plus 3 times an x squared minus 4. All over an x plus 3 and an x minus 3. Okay? Now, obviously, our domain here is that x cannot be negative 3 or positive 3. When you have that, you need to include those on your sign diagram along with the critical values. Okay? So, let's actually look at that. We know our sign diagram is going to have a negative 3 on it and a positive 3 on it, just from the points of discontinuity. Notice that one of those would be a hole and one would be an asymptote, right? Which one would have been a hole? At x equals negative 3, because it would have reduced out with the numerator. But even though that happens, okay, even though that happens, it's still eliminated from the domain, because we have to look at the original function. Now, let's consider our derivative. Because this does reduce, remember you can find the derivative by taking the derivative of the reduced form, okay? As long as you keep in mind that x is not allowed to equal a negative 3, okay? So this will make our quotient rule a little bit easier to work with. U is x squared minus 4, v is x minus 3, so u prime is 2x, and v prime is 1. So f prime of x is u prime times v. Oh, sorry. Need to make sure I use the correct v. V in this case is x minus 3 because we're using the reduced form, minus u, x squared minus 4, times v prime, which is just 1. And that's all over x minus 3 squared. Okay? So, I'm going to distribute and combine like terms. I've got a 2x squared minus an x squared, which is x squared. I've got a minus 6x. And I've got a plus 4. And that's all over x minus 3. Squared. Okay? So now, to get our critical values, what do? Factor the top if we can. If it can't, got to use the quadratic formula.
I think you have to use quadratic formula.
Huh?
I think you have to use quadratic formula.
Yeah, we will. Because the only way to factor that is either with a 2 and 2 or a 4 and 1. And both of those aren't going to give us 6. So yeah, so we've got to get, for our critical values, x is going to equal 6 plus or minus the square root of 36 minus 16 all over 2. So 6 plus or minus the square root of 20, which is 2 root 5 all over 2. So our critical values are 3 plus or minus root 5. If you know that root 5 is approximately 2.2, then you know you have 5.2 or 0.8. Okay? Now, you guys know how to do this. I'm just doing it a little faster than you might, okay? And that's okay. This stuff is the algebra you know how to do. You just got to work through it. So let's get to the actual calculus. Now we're putting this on our sign diagram. Here's our 0.8, and here is our 5.2. Okay? Now remember here, negative 3 gave us a whole, and this positive 3 would have given us an asymptote. This was a critical value, and this was a critical value. If you want to label those kind of like that, you can, just to help you remember. Okay? Because here we go. We've got 5 different intervals here. We have everything below negative 3. Alright, so if I plug in, let's say f prime of negative 4, I can figure out the sign there. I have between negative 3 and 0.8, so that's nice. 0 fits in there, f of 0. And f of 1, or sorry, not f prime of 1 would fit in the next interval between 0.8 and 3. F prime of 4 would fit in this next interval. And then we could do f prime of 6. Sure. By the way, notice being able to use your calculator efficiently, like with the store X, or even just graphing it and just tracing and hit type in the numbers you want. That is an easy way of evaluating as well. Okay? Or even put it in your y equals and make a little table for yourself. However you do it, though, you need to be able to use your calculator efficiently. Okay? If you don't have the calculator, you can do these in your head relatively easily. Notice on the bottom, it's squared. So no matter what I plug in, it's going to be positive. So really all I have to check here is my numerator. Okay? That's another thing that can save you some time. I don't care what this is, because it's always going to end up positive. So this will determine whether my function is positive or negative. I should say whether the derivative is positive or negative. Okay? Now, if I plug in negative 4, I have 16 plus 24 plus 4, whatever that is, I know it's positive. Okay? If I plug in 0, I get positive 4. Okay? If I plug in 1, I have 1 minus 6 plus 4. That's negative 5 plus 4 is negative 1. So I know it's negative. If I plug in 4, I get 16 minus 24 plus 4. That's 20 minus 24. That's negative. Okay? And then if I plug in 6,
Positive.
36 minus 36 is 0 plus 4 is positive. Okay? Now notice here, don't jump to conclusions. This is why it might be helpful to label these on your sign diagram. Because
they're not plateaus.
Very good. This is not a plateau point. Let's look at what this would look like here. Okay? The whole is an actual point, and if we plug negative 3 into the reduced form, we actually get the whole to be negative 3, and then 9 minus 4 is 5, negative 3 minus 3 is negative 6, so it's a negative 5/6. Okay? That's our whole. remember you plug in the x value into the original, okay, after you've reduced it. So if I'm graphing this, watch what's happening here. I have an asymptote at 3. I know my y-intercept is negative 12 over negative 9 if I go back to the original function, which is 4/3. So I know I'm going to hit the y-axis right here. Okay. I know I have zeros at 2 and at negative 2. If I look at my reduced form here, that's going to be 2 and negative 2 will make it 0. Alright? But then I have all this other stuff I have to take into account. I've got a hole, I said at the point negative 3, negative 5/6. So here's negative 3, there's negative 1, so negative 3, negative 5/6 is right there. So let's look at what we've got at the critical values. Okay, this critical value I'm increasing before and I'm decreasing after. So that means that that 0.8 will give me what? A max point, because I was increasing, then I was decreasing. So if I plug in 3 minus root 5 into my function, okay, let's see here. We have a 3 minus square root of 5. Okay, I'm going to store that in x, and I'm going to punch that into, again, the original function. So x squared minus 4 divided by x minus 3. Okay, that's a 1.527 or 1.53. Okay? So I know that I have a max at the 0.8, 1.53. Okay? So let's put that in. 0.8, 1.53. I know that the y-intercept was 1 1/3. So it's going to be just above that. Here's my 0.8, 1.53. Okay? Now again, if you look at this critical value, I'm decreasing as I approach it, then I'm increasing, which means 5.2 gives me what? A min point. Okay? So if I store that in x, and I do x squared minus 4 divided by x minus 3, I get 10.47. Oops. Now this one is a little bit of a paradox. Because check this out. When we put in the 5.2, we get a 10.47 or 10.5, but that's supposed to be a min, right? Let's look closely at this and see how that can happen. All right, so there's 1, 2, 3, 4, 5.2. So 5.2, 10.5. We'll make 10.5 up here. Okay, and again, that's a min value. Okay. Here's where we've got to look carefully at our sign diagram. I am increasing. So I started down here, I'm increasing to my hole. Then I continue to increase through the 0, through the y-intercept, until I hit that 0.8. Okay? So here's my function so far. Okay? Now that I've hit my max, I start to decrease, and I go through the 0, of course. But notice I continue to decrease, and this is an asymptote, so I'm going to approach that asymptote but never cross it.
And then it starts up again.
Inversely down.
Where does it go?
Infinity,
Yeah, up.
positive infinity.
It goes up, since I'm approaching the asymptote down to negative infinity, when it crosses the asymptote, we've seen this a lot, it jumps up here to positive infinity, and that's how I can have a min value that's actually higher than the other max value. Because these are what are known as relative max or min points. Or we could also call them local max or min points. Okay? So it's going to look something like that. Alright, and that's what that graph would look like roughly. Does that make sense?
How did you find out that 3 was an asymptote again?
That was just from our original function. After we reduced it, we still had an x minus 3 in the denominator. And that anytime you have something eliminated from your domain that doesn't cancel, if it cancels, it's a whole. If it doesn't, it gives you an asymptote.
Right, okay.
Okay. Alright, so there's a lot to this, guys. But a lot of it we've actually done in the past. A lot of this is not even calculus. It's just, you know, get your zeros, get your y-intercept, all that stuff to help you. But then you're getting your derivatives to help you find the exact max and min points. Okay? Alright, so that's one thing when you have a sign diagram and you have a limitation on the domain. Okay? So, I kind of mentioned this already, and we've used this a couple of times, but I just wanted to lay this out to you, because this shows up quite often on the IB exam. I've seen this a lot. They'll say, show that something is a max or min point, and you have one of two options, and you've got to do all the parts to this, okay? The first thing you've got to do is prove that that's a critical value. Prove that the x-coordinate of whatever point they gave you is a critical value. Then you have to show that at that critical value, either number one, you're changing from increasing to decreasing or decreasing to increasing, or, and this is something we're going to do later when we look at second derivatives, you can show that the second derivative is positive, which would make it a min point, or negative, which would make it a max point. And we'll look at why that is later. But this is one thing you've got to keep in mind. It's just kind of a process. If you're trying to prove that something is a max or a min point, or even a plateau point, if it's a plateau point, as we'll see, f prime will not change signs, okay, at that critical value. And in fact, the second derivative will equal 0 as well. So, just something I wanted to lay out there for you. Okay, so here's kind of a process. We're not going to redo this entire one because we just did this. Alright? But this is kind of the process that we could follow. Alright? If we're trying to make a detailed drawing or sketch of a function, I recommend kind of following this path. Alright? Do the stuff that we did back in pre-cal honors first. Get your y-intercept, determine the domain, and also determine which of them are asymptotes and which are wholes. Find your zeros. This is obviously not required, but it can be helpful. Okay? Then, find the derivative and critical values. Use a sign diagram to find the intervals where it's increasing or decreasing. Okay? And by the way, one comment I'll make here is if you are told to give the intervals, just showing the sign diagram is not good enough. Okay? If you remember the sign diagram, we had to -3, and then we had to 0.8, was it 0.8?
Yeah.
And then to +3, and then 5.2, is that right?
Yeah.
And it was increasing, increasing, decreasing, decreasing, increasing.
You need to find a point where it actually hits.
Yeah, so if I'm telling the intervals where it's increasing or decreasing, I'm going to say, all right, this is increasing from -infinity to -3, also from -3 to, it was 5, or sorry, not 5, 3 minus √5, okay?
Can we just say 0.8?
I didn't give 3 sig figs on that, so I would use the actual radical. I don't remember what it is out to 3 sig figs, so if you give exact, you don't have to worry about 3 sig figs. And then also it's increasing once we pass 3 plus the √5, that 5.2, all the way to infinity. So I have 3 intervals here where it's increasing. And then I also have it decreasing
From 3 minus √5 to 3.
good.
And from 3 to 3 plus √5.
Yeah, there you go. Okay? If you're asked to give the intervals, make sure you give the intervals. Alright, I have a lot of students I see, they do the whole sign diagram, they did all the hard work, they just didn't write their final answer and actually give the intervals. Okay, so those are some easy points. Don't lose those. Okay? Alright. So at this point, we're just going to stop and use whatever time we have left to practice some of these, getting those critical values, doing sign diagrams, identifying max and min points, and doing some sketches. Okay?